Hello, and welcome back to part 2 of how to prepare for your chemistry lab practical. So in this particular set of the videos, rather than going through the conditions of the practical, we're going to be going through every lab and talk about kind of the major things that I would recommend studying for as we go through the practical. So one thing is you do need to study for this just like any normal exam, even though it is a lab-based exam. A lot of people are like, oh, how do you study for a practical? The best thing for you to do is to review mainly review the introductions of your different procedures. And then I would recommend like flipping through the data sets to see like, okay, what did you calculate? Especially those older labs from the beginning of the semester. Some of them you haven't seen in maybe 2 or 3 months. So it's really easy to forget some of those core concepts. So go through them, flip through them, see what they are. And I would practice some of the post-lab questions and some of the data workup you did and make sure you're getting the same numbers that you got from before. That's the best way to practice. Now, the other things is as we go through these videos, so as you're watching this either via Canvas or on YouTube, if you're on YouTube, I did mark each individual experiment, which I'm referring to for you to kind of see what I'm talking about. So if you're only looking for specific ones, you can kind of scroll through that and look for them specifically. And just as a final, as a little, warning, I'm not going to say every single detail, which could be on that practical. If we were to do that, this video would be hours long. There obviously could be more, and every teacher's going to test you on different things. So these are just the major things I would recommend knowing, and they're going to help you with your final exam and maybe even your last exam too. So it's going to help you with all kinds of things. So let's take a look at each exam and each lab and see exactly how we would prepare. So the first experiment that you performed was making measurements back in week 1 or week 2 of your semester, a very long time ago. So with this lab, it went over some core concepts that were used throughout the entire semester. The biggest thing is you need to learn how to make different measurements of mass, volume, and length. So when we're making those measurements, the biggest thing is when you're taking your practical, you need to record all of your significant figures and your units when you are writing down your answers. If you do not write one of those things, you might lose points on questions, and you might have got the answer right, but you didn't write your units or show your work. So make sure you write all those things down. They're very important. So when you're writing anything down from the balance, include all the digits. If you're measuring a volume, you got to read your tick marks correctly. So for example, I included a ruler here just to kind of go through like how would you do it. So I put like a little block here, which you had to measure that first lab. So if I were to do this, how exactly would you go about it? So right now I have the block going between 1 and 2. So if we were to kind of look at this thing, you can see, okay, there's 0.1, 0.2, 0.3, 4, 5, 6, 7, right? So the block ends at about 0.7 is where the difference is in that measurement. So is that all you would put though? So the one thing you got to remember is that there was certain digits, so what you can see via the tick marks, and then you could always estimate one beyond that tick mark. So that last digit is fully up to you what you want to place, but you need to include it. So even though it's 0.7, in this case, you'd have to put 0.70 to indicate the sig figs, right? Trailing zeros are significant, so you need to place them. It matters, right? If you are using a very accurate piece of equipment, you need to illustrate that and showcase that in your vocabulary. So I'm going to be kind of listing here as like all the important videos and concepts and things that I made other videos on that you can refer to if you'd like. I'm going to put them in the description too, so that way you can refer to them as well in the YouTube video description. So the biggest thing is the displacement method was one of the things that you used. So you measured the volume via length, but you also did the density by doing the displacement method too. So the one thing is when we went over density, it is what we referred to as an intrinsic property. And you're like, oh crap, I forgot about this stuff. So this meant that no matter what the mass was or the volume, it would always have the same density. It does not change. So when essentially like a couple months ago, I made different videos on how to go over this. One was what is density, which just goes over the basic ideas. The other one was a displacement method video, which actually goes through examples of this lab of how to calculate these things. So when we're doing a displacement method, it's actually quite simple. So the whole idea is, just to kind of scroll down here for a second, was essentially you were taking a graduated cylinder with some water in it, and you were dropping an object into the grad cylinder, and it displaced the volume of liquid. So one thing that it allows you to do is, if you can remember, density is grams over milliliters, or mass over volume. So what you can do is, if you measure the mass and then you measure the initial volume, then you drop the object in the liquid, it will displace that liquid, right? So now that displacement is the volume of your object. So one thing that you had to do is you had to take that final volume, minus it by your initial, and then plug it into your density formula, right? So grams over that displacement, and that would allow you to do density. So one thing that when we do this, right, you have to make sure the volume is high enough to submerge your object, but not too high where like it goes over your tick marks. So keep that in mind, right? This is something that is doable in 4 minutes, right? For you to quickly fill a grad cylinder, maybe put something in it. This is doable. Same thing with measuring an object, right? And calculating the volume. Now keep in mind, the formulas would be given to you if you had a cylinder or a rectangle, but you still need to know what density is. That's something that probably wouldn't be given to you, because you should know it because you've been using it pretty much for most of the semester. So let's say if I were to do a simple problem to figure this out. So let's say I did give you a piece of solid material and you weighed it and you found out it weighed 422.1234 grams. So, and then you decide to place the object into 50 milliliters of water in a grad cylinder. The water rises to a volume of 78.2 milliliters. What is the density? So the first thing you're going to do is remember, it's mass over volume is your density. So when we are trying to do that, the first thing we're going to do is we're going to put that mass that was measured, and we're going to put that on top. And then we're going to divide it by the displaced volume. So being that it's always final minus initial. So we had 78.2 milliliters as our final, right? And then our initial was 50.0 milliliters. So we'll take those, put them in our denominator, and that's something that's going to be subtracted. So now once we do that, we subtract those, we divide 422.1234, divide it by 28.2, which is that difference. What you're going to get is 14.9689 grams per ml, right? So that's what you'd want to write. You want to write your units and your number. Now, the thing is, did I get it right though? So yes, my calculator spitted that value out, and sure, that's what it said. It must be right. Thing is, though, you have to be aware of how to round it too. So we got to look at our sig figs. So you can see that the mass had a ton of sig figs. There were 7 here, but the volumes were down to 3. So we always go off our lowest sig figs. So what we would have to do is round it to 3 sig figs. So right under the 9 here. So what it's going to be is 15 grams per milliliter. And I include my units. You box off your answer so that your professor can find it easily. So that way it shows your work. And the other thing to keep in mind is you want to include all your work. Even if you get the wrong answer, include your work. It could award you a lot of partial credit points, especially if you were on the right track when you were doing this problem. Now, the key thing to keep and look out for is make sure you do the displacement, right? It's called the displacement method for a reason. Make sure you subtract your volumes. That's usually the thing that people forget the most. Let's go on to our next lab. Now, the electrons and atoms lab is something that you probably have not even thought about in about 3 months. Now, with this one, the whole idea behind it was you were looking at all these different lamp sources using this little spectroscope that you held up to your eyes, and it essentially showed you like this little rainbow on the spectrum. Now, with this one, there's not a lot in it that's actually doable in 4 to 5 minutes. So this is where you got to kind of be strategic with what you're studying, and especially how much time do you have. So the one thing that you could do is you could use a spectroscope. You could maybe draw what spectra you saw. You could even maybe label different wavelengths that are seen. Now, one thing I put up here is you have to understand the Bohr model too, in case maybe you had a label like increasing energy, increasing wavelength, maybe frequency. Those are things that are doable. There were a couple formulas you used back then, One of them was the not the Rydberg equation. You will probably never have to use that on the practical. It takes a long time to use it. It's something that's a little hard to use in introductory chemistry. So I wouldn't recommend reviewing it, but I would keep in mind, like, make sure you know how to use your energy formulas, your wavelength formulas, your speed of light, just because they are quicker calculations that you can do easily. So like maybe an example, like if I look at the C is equal to lambda times the frequency, which is new. Well, one easy thing you could do is like maybe you got to measure a wavelength and then you got to calculate frequency. Speed of light is always a constant, so maybe you could have to plug in some values, or maybe you measure a wavelength and you have to figure out the energy. There's all kinds of little things that are possible to calculate, depending on what it is that's here. Now with this lab, typically it's generally going to be an easier question if it's something that's given to you, being that most of it is more of a physics lab than a chemistry lab. So let's go take a look at our next one. Experiment 5A was the empirical formula lab, which was probably one of your first more difficult workup labs because it tied in the concept of the mole, empirical formulas, molecular formulas, a ton of new equipment. It was kind of like your first real chemistry experiment that you had to do. So the first thing that's a very common question that could come out of this one is recognizing your glassware and equipment. So one thing you got to keep in mind is generally on the first page of your lab manual after the table of contents is a list of what all the equipment looked like. Now they're drawings, they're not the best pictures, but it's something to study off of. So making flashcards with the pictures and the names can be really helpful. It's the easier question that if you have that one, you want to get right, especially if it's worth 5 points or 10 points, depending on what your questions are worth. You want to answer those ones, especially if like maybe your strongest suit is not the math part, or maybe you don't know how to do pH, or you don't know how to do something, right? You need to make sure you get these points, or the easier points. So a couple of things that we learned about, right? We learned about the Bunsen burner, so that's on the far left here. So that should be familiar. Other things we use a lot, we use ring stands all the time. So if you had to identify that, clay triangles were used to hold our crucibles on. So if you kind of remember, this guy sat on top of the triangle, and then that went on top of the Bunsen burner flame. We also had iron rings that we used as well. So like the triangle would sit on the iron ring. So just kind of remembering that these things exist. There was the crucible tongs, which were used to take this off, because you remember your fingerprints never wanted to be on it. And then you had the wire mesh that you could sit that on to help cool it down. So there was a lot of things. Now, with this experiment took 15 minutes just for one iteration of it. And you had to do it 2 or 3 times to heat it. So the whole experiment took about an hour. You're not going to have to do that, right? That's not something doable in 4 to 5 minutes. But recognizing things is doable in 4 to 5 minutes. Now, other things to keep in mind, like what other questions could you ask? Doing an empirical or molecular formula is the main goal of this lab, but it's something that is a very tricky calculation. It might take, this would be your hard question if you had it. So depending on your version, you might. So if that's the case, I would recommend going to my empirical and molecular formula video. It's a 16-minute video if you want to kind of just fast forward to the part where I go through an example, and I try to actually base it off this experiment when I made the video. So that way you were a little bit more ready for that lab when you were getting to it. Other things you might have to do is the molar mass, right? Can you find a molar mass? Can you find a number of moles? Can you do those basic stoichiometry calculations? Because if you can't do those, that's really concerning towards your professor, right? You need to know the basics in order to pass. Another thing that we also did in that lab, in the post lab, is there was a lot of percent composition questions, which was how much of a molecule is this particular element or this particular ion or whatever contained inside of this. So that's another thing that it would be worth your while to refresh yourself in how to do those part over the whole calculations for a formula, because it will help you study for your final exam as well. So let's go look at the next lab. Now, when it comes to molecular modeling, which was experiment 6, this was one of the earliest labs you had to do where you first started to learn about how chemicals are bonded together. So the only thing you could essentially pull from this lab is how to draw a Lewis structure. So this could come in a couple different ways. One, you could be given the chemical formula and you have to draw the Lewis structure. The other one is maybe you're given the model and you have to draw what the Lewis structure would be of the model. Depending on your teacher, you might have also had to identify the Vesper structure. But if that is something you have to do, you would be given a reference sheet to help you identify the actual geometry. But let's say if you had to, let's practice this real quick because maybe it's probably been a while since you had to do Lewis structures. So the first thing you had to do is find the central atom, which I always like to say is what has the most friends. So looking at your bonding trends, oxygen can make up to 2 bonds, hydrogen can make 1. So in that case, oxygen can have more friends. So when you draw this, the first thing you're going to do is you're going to place all of its valence electrons around it. Oxygen has 6 valence electrons, so we're going to add 6 dots all around that structure. Now, the next thing we're going to do is we're going to place the hydrogens. And you always want to put the bonds in line with where those single dots are because your goal is a pair. So we're going to put a hydrogen on the bottom here and then a hydrogen on the left. And if you drew this and you put them in another spot, that's fine as long as it's showing that each hydrogen has 1 valence electron and they're on their own. Now, the next thing you're going to do is you're going to connect all of these different bonds. So we have one bond that's right here, and then we have another one on the side. Now, after you do that, you want to count to make sure you have all your valence electrons, right? So we have 8 valence electrons for this molecule before we connected everything. So when you're doing this, you just want to kind of double check, make sure you got everything, right? We have 1, 2, 3, 4, 5, 6, then 7 and 8. So everything's accounted for. We have a correct structure. Now with CO2, once again, a lot of times that the central atom is written first. So in this case, carbon is your central. So carbon has 4 valence electrons around it. So we're going to write those 4 dots. And then what we're going to do is we're going to place our oxygens on each side just to kind of make it a little symmetrical. And then we're going to add the 6 dots on each oxygen because it has 6 valence electrons. So we got that. Now, the thing about these is, if you remember, is that you all want to obey the octet rule. So we'll connect everything with a single line first. And what you're going to see is nothing obeys that rule of 8. The carbons don't, the oxygens don't, so they're all really mad. So what we're going to do is we're going to make double bonds first to see, hey, can you make everything more satisfied? And when we make one double bond, it makes the oxygen on the right happy. And then let's say if we make a double bond on the left, it's also going to make that happy. They all have 8 now that they're all sharing. Carbon has 4, it's giving 4 electrons via bonding, and it's receiving 4 as bonding, so it has all 8. And then you see the 2 lone pairs around oxygen, and then you have the 4 that are being shared in the double bond. So it has its complete structure. So this would be how you draw the Lewis structure for both water and CO2. Let's look at our next lab. The calorimetry experiment was also a very data-heavy lab, which had a lot of workup. The good thing about the calorimetry lab, I guess, is that it was actually fast. So meaning it's something that is doable within a 5-minute period, because all you were doing was mixing different solutions together and seeing, is there a heat change? So there was a couple different things that were possible. Now with calorimetry, if you don't really remember it really well, I did make a video just on calorimetry, and I did try to title it lab-based examples because I went through very similar examples to what you did in the lab to try to help you with calculations. So with this thing, the whole idea is being able to recognize first what the system looked like. So this one, we had 2 coffee cups, which were sitting nested in each other. And then we had a little cardboard lid on the top here. And what you did is you mixed a bunch of solutions together. You would mix them together and you'd be measuring what the temperature change was. Whether the temperature went up or went down told you some stuff about the science. So what are some things that I can think of that you would need to know? So the first one is, well, make sure you really know how to use the MCAT equation, which I wrote up here, right? knowing M is mass, C was the specific heat, which usually probably a lot of you forgot about that. That was how much heat is required to heat up 1 gram of a substance by 1 degree Celsius, and then times that by the change in temperature. So that is something you have to do, and we'll go through an example of that. Now, I would recommend knowing your units for this one. Mass is in grams, C is usually in joules over grams over Celsius, and then T is in Celsius. Now, make sure you know how to read a thermometer, right? Once again, tick marks and sig figs are important. They will ding you on wrong answers when it comes to answering these. Now, the other thing is knowing how to do a change in temperature, right? Whenever we have a delta, that's a displacement or a difference. So that's final minus initial, right? It's always in that order. Now, the other thing is to keep in mind is remember exothermic and endothermic. If the temperature goes up, meaning it's releasing heat, it's exothermic. If the temperature is getting colder, that means it's absorbing heat and it's going down, right? So that's what you're going to observe when you're looking at those numbers. So the big thing is like know how, one thing that's easier to do is like maybe you might have to make this and do observations. But another one is, can you manipulate the data, which is usually the harder part. So when it comes to trying to calculate these, right, you might be given a data set and you need to be, and you're told, solve for heat. Could you do it, right? So you got to be given the values. So the first thing is you always take your total mass of the solution. So that will be your mass in that MCAT equation. So we have Q, MC, delta T. So what we're going to do is we're going to take our mass, which in this case is 40.1234 grams. We're going to multiply that by C, which is 4.184 joules, grams, C. And you want to write down all of your units while you do this. So that way you get the maximum number of points while you're going through it. And then you're going to write down times Celsius. And then you're going to notice that, hey, your units are canceling. So that's going to give you an idea that you're doing these correctly. So that's good. So once you multiply 40.1234 times 4.184 times 30, you're going to get about 5036.3 joules. So once again, is this the correct answer? Technically, from your calculator, yes. But we need to show the correct sig figs. So one thing you'll always look for is the one with the smallest number. So we have 3 sig figs from your temperature. So we got to round it to 3 sig figs. So what this is going to be is 5040 joules, or you can show it in kilojoules or scientific notation, whichever one, it makes essentially like makes you happy here. So I'm sure all of them will be accepted, but it just kind of depends on which one you want to aim for. Let's look at our next experiment. All right, experiment 11B, which is determination of the gas constant. So with this one, it's one that like a lot of people tend to forget about just because it's been a minute. And it also was a very, very quick experiment too. So it only lasted about 45 minutes. So with this one, it's something that takes a little too long, once again, for you to physically do it. But there is a lot of measurements that you could take in this one. One of the easy ones, once again, is the thermometer. Make sure you're able to read it. The other one is know how to use a gas collection tube, right? So if you remember, you had a big tube that what you had in it was magnesium inside of it. And when it reacted with HCl, it made a ton of gas. The gas pushed out the water, and then you measured the volume of gas that was in here. So make sure you're comfortable in reading that volume. It's in milliliters, so keep that in mind. Know your units, so you know how to read those different pieces. Now, there was a couple other things that we used in order to read things too. One of them is being that this was a gas law lab, you have to measure pressure, right? So we got to be comfortable with that. Remember, there's a bunch of units for it. There was millimeters of mercury, there was torr, there was atmospheres. So I'd recommend kind of refreshing yourself with that. The most common in our class were atmosphere and millimeters of mercury. So make sure you're comfortable with going between those two units. Now with them, we used a couple different reference materials to measure pressure. The one is we had a digital pressure gauge, which told you the pressure of the room. The other one is we had a book that told us what the pressure of water, or the partial pressure of water inside of this container. So I would recommend going through and reviewing those different concepts. So you might have to use the ideal gas law because you can figure out the pressure from from maybe the scales, the volume from the tube, the temperature from a thermometer. They're all things that could be put in front of you, right? Now, the one hard part is making sure you remember how to use Dalton's law. So usually you want to use whatever your gas is as one of the pressures, and generally the other one is water, which is where that book came from. So what I would really recommend is there's a lot of videos that I kind of made that use this concept. Being that it does tie into gases, it's possible to see gas stoichiometry in this as well. I would recommend kind of reviewing percent yields too, just because it's something that can get tied in. So there's kind of a few things you could review. One could be the ideal gas law, Dalton's law for sure, just because this is probably one of the more comprehensive videos. It tied these two things together. So this one is a really good bet for reviewing. And then there was the two stoichiometry videos, which I released like a few weeks ago. So with these two, right, there's part 1 and part 2. Part 2 has to do with the ideal gas law, so that's more relevant to this lab. And then percent yield is if you have to figure out a theoretical yield or how much was made and how much was collected. You had to do these more in class in terms of calculations, but it is an important concept in lab too. Okay, so let's look at our next, let's look at our next example. So with our next one, which was experiment 9, this one you had to make a standard solution scheme, just like the one that was in your lab manual, right? You had to take the densities and plot it against molarity values, which you found. So the first thing is you need to know molarity. Like there's no way around that. That's one of the things I've been trying to say like for weeks in terms of videos. Moles over liters. You have to know how to do it because we've done probably about 3 or 4 labs that involve molarity. Be confident in it, practice it. The dilution formula was a big thing, right? If you have a solution and it's way too concentrated, meaning like I was using an analogy, it's too sweet or too salty. So what do? You add water to it to dilute it. So that was something that was really common you had to use. This is a formula that's generally assumed that you know off the top of your head, just so you know, because M1V1 equals M2V2 is a very, very common formula. So especially if you are someone that makes solutions in chemistry, bio, or health sciences, it is very common. So sometimes this formula is not given. It's probably one of the few that's not given. So I would recommend just knowing it off the top of your head. It will help you. Be comfortable in how to make solutions and what was involved with using them. So the big thing is we use the volumetric flask, right? So knowing how to use it, how to identify it, right? It has a teardrop shape to it. So you can kind of see like the teardrop bottom here. We had 2 kinds of pipettes. There's a transfer pipette, which is just for moving liquids around. You don't use it to measure. Then you have your volumetric pipette, which was always labeled with the actual volume. And that one was a very precise piece of glassware. If you remember, it went down to 2 decimal places. So that's really important to realize. And then we went through density, molarity. We made a calibration curve. So there's all kinds of things that could be used here. Being that we talked about density earlier, and we also kind of we'll do a little bit of molarity in a little bit. Let's talk about how to use that curve, right? So this was one of the things that you had to plot, right? So you took the time to make it and you had to use it. So you had to measure an unknown solution, and you figured out its density. So if we do this example and I ask you what is the molarity of a solution with 1.021 grams per milliliter as its density, how would you solve it? What would you do here? So the thing about this curve, right, is how is it all labeled? Well, you got to kind of remember, right? We have the y-axis, which was on the left-hand side, and then we had the x-axis. So what we were given is we were given a density, right? That's a y value. Now, one thing about this is you notice that there's this line that's going up and down the actual graph. That's referring to this y equals mx plus b formula, which is something you can use to find the concentration, right? Because you notice there's an x value and a y value. So what you can do is you can plug your value into that. So what we have is 1.021 grams over ml. And that's going to be equal to the other part of the formula, which is 0.435 x plus 0.9984. So what you would do is rearrange this equation and solve for x. So if we were to do that and we were to solve for x, just like so we're going to subtract our 0.9984 and then divide by our 0.435. That would get x by itself. So when you solve for that, what you are going to end up getting as a number is you're going to get your molarity, which is going to be 0.5195 molar. And this is something else you can round to sig figs. So being that everything was 4 sig figs in the data table, you would end up rounding this to 4 sig figs. So this is the idea, right? Can you manipulate data? Can you read data? That's important, right? Because you've been doing it all semester. So you got to be confident in it. And like I've been saying, like if you've been doing your labs, you've been doing the work, you will get a good grade. But you still got to review for it. You don't want to go into it and be like, oh, I got 100 on every lab, but I failed the practical. Like that's crazy, right? You need to practice your skills. So let's go to the next one. The next one was types of reactions. So experiment 10A was a very, very intensive data workup lab. It was really fun kind of going around mixing things together for about an hour. But the one thing you notice is that the data workup for this took hours. You had to write all these net ionic equations, predict all these reactions, balance all of them. But there were skills that you need for this class, right? You're using them all the time in stoichiometry. So you still use them and it doesn't go away. So the first thing you got to make sure you're familiar with is know your types of reactions. Can you predict your reactions? And this is something sadly you do not get notes or a reference for. So you need to kind of know at least the fundamentals. Can you do a combination, decomposition, double replacement, single displacement? Can you do them? The other thing you need to be familiar with is the scheme 2 based on observations of what you're seeing. So like, did a gas come off of it? Gas evolution. Did a solid form? That's precipitation. So that way you know how to label things correctly. You will have to predict products and label the reactants. Can you balance it? If I give you a complete form, if I give you the whole formula, can you balance it? Can you label the states of matter based off what you saw? Or can you write a net ionic equation if I give you the solubility rules, right? Now, even though this is not in this lab, all this stuff, these skills will lead to stoichiometry, which is essentially the pinnacle of the course, right? It all leads up to stoichiometry, which ties everything together. So can you try to relate all these things together? So I put a solubility table here because one thing that we're going to practice real quick is, can you write a net ionic equation, right? So can we do the whole process from start to finish? So the first thing is, right, is you want to write down your reactants of what's going to be mixing together. So we have barium chloride and then sodium sulfate is here. And what they're going to be doing is mixing together to make a new compound. So the first thing we always do is we assign our letters to each ion. So barium is ion, chlorine is an ion, we have sodium and then sulfate. So it's AB plus CD. So what is that? That's going to be a double replacement reaction. So what we're going to have bond together is the inside is going to bond, and then the outside is going to bond together. Now, the thing to remember, cation is always written first. So we'll take sodium. We do not write the subscript here. We just bring the ion. And then same thing with chlorine. We'll bring that over as well. So just the ion. So notice how they're balanced with their charges. So we don't have to worry about swap drop. And then we'll bring over barium and sulfate. So BaSO4, and that's 2 plus and 2 minus. So that's balanced in terms of charge as well. Now, the next part is we're going to balance our formula. So you'll notice is that there's 2 sodiums and 2 chlorines on the left. So what we're going to do is put 2 on the right. And now we have a balanced, complete molecular equation once we remove all those charges. Now, the next part is using your solubility rules. So the first thing is we have barium chloride and sodium sulfate. So one thing you'll see is if we look for our different ions, so we have chlorine here and then sulfate. It says chlorine is soluble except when it's bound to some heavy metals. So that one's good. And then we have sulfate is soluble except when it's bound to calcium, strontium, or barium. So it's soluble with sodium, but not with barium, which was our other one. So with these, what we can see is what was soluble is the barium chloride is aqueous, sodium sulfate was aqueous, sodium chloride is aqueous, but our last one, which was the barium sulfate, is a solid. That one's insoluble. So now we're going to break everything down into its ions. So the barium will break down into an ion. So we put barium 2 plus, then we'll have 2 chlorines, and 2 sodiums. It's like we're smashing all these pieces because they are soluble in water, right? So everything's breaking down. And then the only thing that stays together are solids and gases. They stay together. So now when we have that, when those things stay together, you will pretty much, you're going to leave them there for the very last part of the reaction. So we're canceling out anything that's a spectator, that's identical on the left and the right. So the things that you'll see is that, okay, there's 2 chlorines, there's 2 sodiums, they're the same, they're just watching. So everything else stays in the net ionic equation. So there's barium, sulfate, and then that's all leading to barium sulfate. And that's how you would write a net ionic equation, right? Of all those pieces of the puzzle from start to finish. This is a longer one, so if you had to do this one, this would be your hard problem for your example, is doing a net ionic equation, because it takes a long time. So let's go to our next one. So with experiment 12A, with the pH of household chemicals, the whole idea here is you need to be able to understand the basics of pH and how to do the different calculations behind them, and also understand how to use red cabbage as an indicator, or realistically any indicator. So can you calculate pH, POH, H3O plus, OH minus? Can you calculate all these little pieces and use all these formulas? Now, the thing about this, you will be given these formulas if you have to use them. So, but you need to be able to like read a chart that looks like this. So if I were to, let's say, do one of these, let's say I want you to solve for POH, OH minus, and H3O plus, and I give you the pH. So if we start up here in the top right corner, we can follow any road to get to the other pieces. So for example, if I have pH, the easiest one to solve for is POH. All you need to do is take 14 minus 4.30, which was our pH, and then we would get our POH as 9.70. So we have one of the parts. Now from there, in order to go from either pH or POH to its concentration, we need to do 10 to the negative, either 10 to the negative pH or 10 to the negative POH to solve for the other parts. Now with these, the hardest part is sig figs. So if you kind of remember, if there's 2 decimal places, that means you have 2 sig figs. So in this case, what we're going to end up having for the one on the left is 5.0 times 10 to the negative 5 is going to come out as your molarity for the left one. And then on the other, you're going to have 2.0 times 10 to the negative 10 molarity on the right. So these would be all of your values for this problem if you had to solve it. And it's something that's quick and doable. You have your calculator to do them, but you have to be familiar with how to use those formulas. Let's go on to our last one. All right, so experiment 12B, which was the one that we've done the most recently. The big thing about this is this probably should be the freshest one in your brain, so you should be familiar with how to do it for the practical the best. With this one, there was a lot that was being done in this lab. The first thing is knowing your glassware, right? The first thing is we had some new piece of glassware. We had a burette, and then we also had an Erlenmeyer flask. That was the first time you were using those. So make sure you're able to identify them and to know how to read them, right? Especially the burette. You have to know how to read an initial and a final volume, how to read how much was used. That's a big part of this. Now, there is some vocabulary that was introduced in the introduction. So the first thing is there's the word titration, meaning that you're taking an acid and base, you're canceling them out. There can be other chemicals, but in our case, it's an acid and base. There's one word that in lab that I mentioned to some students, but not everybody, but it's the word titrant. This is the chemical that you know the volume and the molarity of. So for us, that was sodium hydroxide. Standardization was what we did to find that molarity. So that's another concept, being familiar with those terms. We've had to find a molar mass of a hydrate. So that's something that kind of refresh your brain on in case you forgot. I do have in my molar mass video, I do go over that. Make sure you know how to read that initial and final, know the volume you use, and be able to perform solution stoichiometry, right? So if you were not too versed on stoichiometry, if you're behind, you really should look at some of the stoichiometry videos before the actual before the test, just because you know there's going to be at least one of those problems you're going to get is going to be stoichiometry. At least one station will be. So you have to do something, either whether it's mass to mass or solution to solution. There's going to be something. So these two videos that were recent, the one was acid-base titration, and then solution stoichiometry that you could view as well. So with our last example, that to cover the rest of the video, if I ask you what is the molarity of sodium hydroxide if 25 milliliters is combined with 0.1000 grams of acetic acid. So with these, the big thing is you got to be able to kind of remember your mole maps. So the first thing is like you got to ask yourself is, well, which one can I get to moles with? Can I do it with a mass or with a volume? The only one that you actually can is a mass. So if I have a mass of, let's say, an acid in this case, the way that we can convert that to moles is using the molar mass. So if I have molar mass, which we were given, we can convert from mass to moles. So let's put that down. So we have 0.100 grams of acetic acid, so HC2H3O2. And what we're going to cancel that out is the molar mass. Okay, so we have 60.021 grams, equivalent to 1 mole of our acetic acid. Now, the next part is, well, how do we get 2 moles of our sodium hydroxide? Well, this is where the chemical formula comes into play. So one thing you'll notice is that it's a 1-to-1 ratio. So what we can write is that we have 1 mole of acetic acid, so HC2H3O2, and that's equivalent to 1 mole of sodium hydroxide. Now, the thing is, though, you're not done because you need to figure out your molarity. This is where earlier I said you got to know molarity, right? It's moles over liters. So we're going to solve for the moles of sodium hydroxide. So once we do 0.1 divided by 60.021, you're going to get 0.001666 moles of sodium hydroxide. And then we're going to divide that by our volume, which was 25 milliliters, and we're going to convert that to liters. So we have 25 mLs. We'll quickly convert that to liters, and then we'll divide by that number. And what we're going to end up getting is 0.06664 molarity of sodium hydroxide. And the thing about that is you could solve for pH, you could do all that stuff too, but that would be a little bit of a longer problem. So we're not going to do that in this video. That's in my other videos. Okay, this was a very long review video, but hopefully it does help some of you, those of you who were able to grunt through it and make it through it. I try to go through a little bit of everything with all of it. So it's my first time trying to make a review video for all this stuff. So try to study hard. I hope that this did help a little bit. And please let me know if you need help until you're practical, and either reach out via email, Discord, comment below, whatever you need to get a hold of me. Okay. All right, y'all. I hope you have a wonderful day, and I'll see y'all later. Bye now.